Nee, aber ganz kurz noch. Auf Entstummen. Okay.
Okay, I guess that's on, right? Good, welcome to our seminar. So it's a great pleasure to have Sylvester, BORSBOOM here actually speak today about gauge symmetries and special asymptotic boundary conditions in Yang-Mills-Higgs theory. I should say Sylvester is a PhD student with Klaas Landsman and is it Nijmegen?
Yeah.
So, yes, okay. Well, the stage is yours.
Thank you. Yeah, it's pronounced Nijmegen, but
Nijmegen,
that's all right.
Yeah, I never know.
Yeah, so thanks all for having me. It's a pleasure to be in Vienna. I'd never been here before, so this was a great opportunity to see this very impressive imperial city. Yeah, I've just started my PhD a bit over half a year ago with Klaas Landsman. Though my daily supervisor is Manus Visser, we will work on black hole thermodynamics. So that's not necessarily related to Yang-Mills theory. But this is stuff I did for my thesis, my master's thesis in math and physics, and for which I got these 2 prizes, and since then I've talked about it in various places. So yeah, I'll basically be talking about this idea that not all gauge symmetries are on the same footing. There are some, I mean very few, but there are some that I call global gauge symmetries. I mean, other people have called them that as well, though they've also given it different names like rigid. And these have a different status, basically, than local gauge symmetries. Though it's actually pretty difficult to sort of derive that rigorously, especially if it's asymptotic boundaries that you're talking about, and especially if the theory you're considering is non-abelian. But still, we can do all of that. And then that can actually help us to understand sort of what's really going on in the Higgs mechanism, I think. So yeah, that will be the upshot. I'll first talk about the gauge symmetries themselves and then move on to the Higgs. So I'll also briefly introduce the Higgs mechanism for those that are not familiar with that. So I like to ask ChatGPT for every section to sort of visualize what it's about. So I asked it, what does the Higgs mechanism look like? And this is what it gave us. So yeah, those of you familiar with that will recognize this Mexican head potential that the Higgs field takes its minimum value in. But, you know, this is still not very clear, so we're going to try to make this really precise. Now, I looked at the website of the Müller group and the other groups, but I saw that there's this project on like quantum reference frames and gauge theories and locality. And it included this part saying they'll be concerned with questions such as how's the notion of locality encoded into the structure of subalgebras and operator systems. So that's definitely in the background here, because locality is very tricky in quantum field theory when you have a Gauss law. that sort of ruins it, actually. Yeah, how's locality built into the notion of gauge theory? So that's related to that. But also this question of what distinguishes global from local gauge symmetries is really what I'm focusing on. And then whether there's actually a difference between the classical and quantum scenarios. So there had been people working in foundations of physics who'd sort of said many of these things, but that was mostly classical. And I will show in the end that there's actually been this guy, Franco Strocchi, who together with another person, Morchio, sort of proved everything I'm saying, but then for quantum field theory based on the Weidmann axioms. So yeah, I wrote my master's thesis with these two people, Sebastian de Haro, who's a philosopher of physics, and Hessel Postuma, who's a differential geometer. And yeah, those are also the people I wrote these two preprints with, that this talk is basically a synthesis of. By the way, the first one, I'm like finishing up the second version just now. I hope to put it on the archive before 8 so that it appears tomorrow morning. So compared to the version that's on there now, the new one will contain like a lot more detail on the conformal compactifications for Yang-Mills fields. So that's not really sort of necessary for the main point, but it is important for the details. But yeah, so I started out my thesis wondering, okay, so what is actually going on in the Higgs mechanism? Because there had been this whole debate by philosophers of physics. I'll get into that a bit more later. And there was this one person from Leuven, Bart Struijve, who published this paper called Gauge Invariant Accounts of the Higgs Mechanism. And what he basically does is he considers the Higgs mechanism, the abelian Higgs mechanism, as an instance of global gauge symmetry breaking only. So that's where I got the inspiration from. But then he left many sort of questions open, in my opinion at least. But there was also inspiration actually from condensed matter physics, because in condensed matter physics you have superconductors, which also break gauge symmetry. Actually, it's sort of the exact same thing as what happens for the Higgs mechanism. But that's sort of, you cannot really measure in what direction that they've broken that gauge symmetry, except for the global gauge symmetry. So if you put two superconductors together, then there's this famous Josephson effect where a current starts flowing between them, and that current depends precisely only on the global phase difference of the Ginzburg-Landau order parameters. So that's to my mind also an indication that global gauge symmetries have a physical status, like are physical in a way that the local ones are not. Yeah, and then there's this whole philosophy of physics literature on like the status of symmetries and whether they have direct empirical significance that I looked at. But there was work especially by Henrique Gomez and Aldo Riello on precisely all of this, like the difference between global and local gauge symmetries. The problem though was they do it mostly for, they do it only for finite boundaries, and finite boundaries do seem to be a bit different than asymptotic boundaries. So yeah, I try to use all of this to understand the Higgs, and that will be the main goal of this talk. I hope I actually get to the section on quantum electrodynamics, but maybe that won't work, then you can ask me about it afterwards, because the first sections are classical, and I'll try to at least do that. Yeah, so very briefly, because I love telling this, because so this guy, Kamerlingh Onnes, who he discovered superconductivity in 1911 in Leiden, and I love saying that because he's my great grand PhD advisor. So he's like classes, advisors, etc. Though I actually think that holds like for almost everyone in the Netherlands that's doing physics, but yeah. Yeah, and so later they discovered this Meissner effect, where a superconductor expels a magnetic field. You could, and you can understand that by the idea that photons gain an effective mass inside of the superconductor, and there you actually see the relation to the Higgs mechanism in the standard model, because that's also responsible for giving masses to other particles. But the first explanations came in 1950 with the Ginzburg-Landau theory of superconductivity, and they postulated this formula for the free energy of a superconductor, where psi is the Ginzburg-Landau wave function of the whole superconductor. And they chose the parameters A and B to be such that this energy takes this famous shape of a Mexican hat, right? I don't think I have it anywhere in the slides, but it looks like this basically, except that you can rotate it as well. So yeah, they sort of use that to explain superconductivity, though in a phenomenological way. I mean, the thing with Cooper pairs came later, of course. And at the same time, there was this problem that Yang-Mills theory, which was being used to model elementary particles, would only allow for massless bosons, massless gauge bosons. And then Nambu came up with this idea, like, okay, in like 1961, I think, of maybe we can combine these two ideas and sort of apply the Ginzburg-Landau explanation of superconductors to Yang-Mills fields. It's a brilliant idea, and yeah, it seemed to be promising, except that there was this Goldstone theorem, where you get these massless modes if you break a continuous symmetry, and people were not observing those in nature. And then Higgs and Brout and Englert and Guralnik, Hagen, Kibble, they all independently in 1964 showed that this can be avoided by, like, the Goldstone mode can become one of the modes of the gauge boson, thereby making it massive. So that's basically the history. The way physicists would explain this is as follows. You take a Lagrangian that contains some gauge field whose curvature is f, and then there's a Higgs field phi. It has this potential that looks like the Mexican hat, and it's coupled to the gauge field through the covariant derivative. And then you find this huge symmetry group, namely gauge symmetry. So that means you can transform these fields in a way that depends on space-time points, and the Lagrangian will be left invariant. And then the idea was, okay, so if we now say that the Higgs should be taking its minimum value right here in the middle, at the bottom of the Mexican hat, then we can take that as our vacuum, expand around it, and we'll find a Lagrangian with a gauge field B. So instead of the gauge field A that has curvature F, we now have a gauge field B mu with curvature B mu nu. So that gauge field will actually have a mass term. And yeah, so this is actually how all masses in the standard model are generated. Like it's known that the weak gauge bosons gain their masses this way, but it's actually all of them. So that happens to the Yukawa coupling, which I have right here. So this is the Higgs field, and then these are all matter fields. They also couple to the Higgs. So the quarks, the leptons, they all get their masses from the Higgs. Actually, you can show that any twisted chiral fermion, so that would be a fermion that feels both the gauge fields and is chiral, so its left and right versions are not the same, must get its mass through the Higgs. Like you cannot add just put a mass term in there. That doesn't work. So yeah, philosophers got a bit uneasy about this whole story, because they were saying stuff like, okay, but you're saying that you broke gauge symmetry by expanding the Higgs field somewhere in the bottom of this Mexican hat, and that now that's given all particles in the world mass. But it's always said about gauge symmetries that they're unphysical, right? They don't mean anything. They're redundancies in R descriptions in the same way that supposedly coordinate transformations in GR are. So how can you get mass, which seems very tangible, from something like, well, something sort of entirely mathematically redundant? That was the main sort of worry. And there was this other result. It's called Elitzer's theorem. It's proven in lattice gauge theory, which actually shows that any gauge-dependent quantity must have a vanishing vacuum expectation value. Now, the Higgs field is obviously gauge-dependent, because if I rotate the Mexican hat, the Higgs field is also rotated. So it must have a vanishing vacuum expectation value by Elitzer's theorem. So that's very weird, because it's assumed that the Higgs field has a non-vanishing vacuum expectation value to generate masses. So what philosophers basically wanted was that they wanted to understand what would a gauge invariant account of the Higgs mechanism look like, and preferably we would also like to connect that to the algebraic definition of spontaneous symmetry breaking in quantum theory. And yeah, you can do both, but you have to consider global gauge symmetry breaking instead of local gauge symmetry breaking. That's the upshot of my entire talk. So this famous philosopher of physics, Ehrman, said something along the lines of, "Oh, when we're gonna look at it gauge invariantly, we're gonna find that spontaneous symmetry breaking is quashed. So it will be gone, and confirming that will require detailed calculations, not philosophizing. But if we do the detailed calculations, we find spontaneous symmetry breaking is actually not quashed. It's just reduced to global gauge symmetry breaking." Yeah. Okay, I think. Yeah. Okay. So that was the original sort of what they wanted, the philosophers of physics. Then there were some people who were replying to that, of course. So there was this Bart Struijve that I mentioned earlier, who reformulated the Higgs in terms of global gauge symmetry breaking, but basically left open the question: okay, but why does that not give us the same problem? And then there were these people using what they call the dressing field method. So these are, for instance, there's this Cambridge Elements book by Berghofer and some others, and they have some more articles in which they are saying, so you can dress all your fields. That is very much related to reference frames, as I discovered yesterday. And if you do that, you can basically sort of get rid of the whole gauge symmetry of the system and say, okay, I just have this side of the Mexican hat, and the Higgs field just rolls down. But in that process, it doesn't break any gauge symmetry, and then you can still explain the generation of masses. That's what they tried to do. So basically, there are these two conflicting notions. Either you break the global gauge symmetries, or you give this gauge invariant account. Now, I will try to resolve this tension by sort of following the global gauge symmetry account, but also use the dressing field method, but like on a higher level in a way. So what they tried to do is they said, okay, we should really try to literally get rid of SU2 in the standard model, right? You have U1 times SU2 times SU3, which used to be my Wi-Fi password, and they tried to actually literally get rid of that SU2. I'm saying no, you should get rid only of the local gauge symmetries. So that's a different application of the same method in a way. Okay, any questions so far? No? Okay. Yeah, so let's talk about gauge symmetries then. Does anyone recognize this? It's the Hopf fibration, exactly. Yeah, so it's basically the only nice principal fiber bundle that we know. Well, no, okay, that's not quite true, but it's the nicest one. It's when you fibrate S3 by attaching a circle to every point of the 2-sphere. And it's a principal bundle with structure group U1. It's very beautiful. And these principal bundles are basically the basic objects of gauge theories. So yeah, just to get back to the basics maybe, what are gauge symmetries again? So we always think of electromagnetism to understand this. There you have two fields, the electric and the magnetic field. But you could also decide, now I'm going to write them in terms of another field. I'm going to write them as derivatives of something else. And that would be the gauge field, A. But then you have this problem, like, okay, that's great. I have only one object that they're both defined in terms of, well, okay, so you have A and then you also have the electric potential V. It's the time component of this 4 vector. But then it turns out that is not uniquely defined. So you have this huge infinite dimensional symmetry group that doesn't actually change E and B. So you have to sort of decide, am I going to work with E and B, or am I going to work with A and V and have the symmetries? So both have their advantages and disadvantages, because working with E and B, you cannot really, there are lots of things you cannot really explain, like Wilson loops, for instance. So the Lagrangian of electromagnetism, and this is the exact same for Yang-Mills theory, is actually the electric field squared minus the magnetic field squared. So that's very important for the remainder of this talk, because it means that the electric field is actually a kinetic term. it's kinetic energy. The magnetic field, on the other hand, is potential energy. And we're going to see that that's actually, in a way, very important, because we're going to be putting boundary conditions on both, but then we really have to be careful about what the electric field really is as a kinetic term. It's actually the velocity of something, in the same way that you would have 1/2 mv squared for a particle. And that is going to be very important in defining boundary conditions, asymptotic boundary conditions on these fields. Yeah, so this definition is a bit physical. The mathematical definition would be, okay, we take this object called a principal bundle over some base manifold M. That means to every point you attach some usually compact Lie group, like U1 or SU2. And then you say, okay, but that doesn't really, so yeah, you can trivialize this principal bundle in many ways. And you would do that by taking a section that brings you from the base manifold to a point in the principal bundle. Such a section is called a gauge in the mathematical language. And then the gauge transformations are automorphisms of P, so different ways to trivialize it. And then if you use the gauge to bring the things down to the base manifold, then those automorphisms will make things look different in that gauge, basically. That's basically what's happening. So you have this formal abstract notion of the gauge group as the group of all these bundle automorphisms. But if you are actually working on a gauge, you can view this abstract group as a group of maps on space-time M. That's usually what people do because it's much easier in a way. But it's good to remember that that is only done in a gauge. Whereas the real sort of gauge invariant or independent definition would be the bundle automorphisms. And then if we are working on a gauge, so in this whole thing, I'm assuming the principal bundle to be trivializable, which is very important. It's not the same as trivial, right? It means you can make it trivial, but that act of making it trivial is precisely performing a gauge transformation. Yeah, it means you literally make it m times g, right? So trivializable just means P is isomorphic as a bundle to m times g. Doesn't mean you have actually literally coordinatized this in that way. So here, the way you can think about it is here, we know what the identity element is, right? It's E. Here, this is a homogeneous space. So we do not have a choice of that identity element. So basically, the way you can think of a trivialization is that you pick an identity element everywhere in space-time. Yeah, and so if we do work with gauge transformations as maps on M, with values in the structure group G, so that would be U1 or SU2 or SU3, we can say that what I call these global gauge transformations, they are the constant maps. So other people would call this rigid, like Henri Gomez calls it rigid, because global could maybe also just have the meaning of extending infinitely far, but not necessarily being constant. So this is a bit of a, I chose to stick with global because that's what many people in the physics literature do. So, okay, so this is the formal definition, but this doesn't say anything sort of interpretational, right? This doesn't tell us why we should think of these gauge transformations as being unphysical or redundant, or like states related by gauge transformation represent the same world, right? So all we have is we have this familiar action on gauge fields and matter fields of the gauge transformations, and we know that the Lagrangian is invariant. But what does this tell us about the physical meaning? So one point I do want to note first here is that it's very important that these gauge transformations actually respect any boundary conditions we have on the fields, right? Because imagine you have some boundary conditions, a gauge transformation takes you out of that, so it gives you a field that does not satisfy the boundary conditions, then it's not, you don't have a well-posed dynamical problem anymore. So there is this whole philosophical discussion about Galileo's ship and Galileo's gauge of the physical status of gauge symmetries, But basically, the main point I've taken away from that, and especially this article by Nicholas Tay, is that you should use the constrained Hamiltonian formalism to understand what gauge symmetries are actually redundant. So we'll get back to the constrained Hamiltonian formalism in this section on redundancy and constraints. But first I have to work out these boundary conditions more carefully, because that's actually really important. So yeah, to end this section, what I'm going to do basically in the next part is use this idea that you find, for instance, in celestial holography, which is trying to define a holographic dual for gravity in asymptotically flat spacetimes. There's this general idea that what they call an asymptotic symmetry group, or a physical symmetry group, consists of all allowed symmetries quotiented out by all trivial symmetries. And that corresponds to the language I just used. So the allowed symmetries will be the ones that preserve the boundary conditions. I denote those by GI, where the I stands for invariant, like it leaves the boundary conditions invariant. And trivial, like I said, I'm going to interpret as the ones generated by the constraints. And we're going to see why you would think those are unphysical or trivial or whatever you want to call it. And then there's this quotient of these two that philosophers would call the group of symmetries with direct empirical significance. So the idea is that they are like physical in a way that local symmetries are not. And what well, basically the whole point is to work out that this quotient indeed gives you this global gauge group precisely. So global gauge symmetries are physical, but also all physical symmetries are the global gauge. There's nothing more, right? It's just precisely that. And you might think, okay, that would be very straightforward, because there's this idea that boundary preserving symmetries should go to a constant asymptotically, and the ones generated by constraints should go to the identity. And so you take a quotient, a constant by identity, and it's just, you're left with just a copy of the structure group. But yeah, it turns out for asymptotic boundary conditions, it's actually really tricky. Because you need to care a lot about all the different rates at which this might happen, right? I mean, something could go to a constant very quickly or very slowly, and that might be different for the two, and so it's not clear that you can really take this quotient that easily. But yeah, basically, my point is you can in the end do that and derive this global gauge group. So, yeah, of course. Oh. Yeah. Well, I mean, if you have, yeah, okay. So that is exactly the right question to ask. As I'm going to explain now, a priori, you only demand boundary conditions on the observables, right? Because that's the stuff that matters. That's the stuff that shows up in the energy. But as I'll explain, you cannot do that without also introducing boundary conditions on gauge fields. So that's basically the point that was entirely, that no one ever mentioned, and that my supervisor and I worked out in detail. Yeah, so this is a very good question. I'm going to get to that exactly now. Yeah, so we're going to get to this these asymptotic boundary conditions now, which again I asked ChatGPT to do, but yeah, it didn't do a great job here, I think. This is maybe some kind of conformal diagram or something. So we should find these allowed symmetries, right? The gauge transformations that respect boundary conditions. For me, that will basically mean you want the energy or the Lagrangian to be finite. So the Lagrangian is something like E squared minus B squared, but the Hamiltonian would be the sum, so I want them both to be finite. But that's only, those are conditions in exactly what you're saying, the observable fields, on the electric and magnetic fields, right? Not on the gauge field itself. In fact, since the magnetic field is the curvature of the gauge field, this only, like if I require the magnetic field to go to 0 asymptotically, it only tells me that the gauge field will become flat. It doesn't say anything about like the gauge field itself going to 0. So why restrict the gauge group at all? Because any gauge transformation preserves boundary conditions on E and B, right? Because it doesn't change them. So no one has ever noticed this point, as far as I'm aware at least. So in the literature, it's been said hundreds of times that we need boundary conditions on gauge fields. Like people write down I needs to go to 0 with some order. But why? Because we only need that behavior on the electric and magnetic fields, and those are not changed by a gauge transformation. So why, why take this extra step of actually defining a boundary condition on the gauge field itself, which then gives us the need to restrict G to a smaller subgroup. Yeah. So to understand why you have to do that, we need to look at sort of the phase space of gauge fields. So I'm going to be working in a 3+1 split of space-time, which means I have some Cauchy surface, sigma, and a time axis. And I'm going to be putting the gauge fields in the temporal gauge. I'm going to put A0 to 0 and care only about the spatial part. Now, a Lagrangian, and I'm going to denote this configuration space of all gauge fields, so all the possible gauge fields I'm allowing by Q. And then a Lagrangian is always defined on the tangent bundle to the configuration space, because the configuration space consists of coordinates Q, the tangent bundle has coordinates and velocities, and Lagrangian takes those, right? The Hamiltonian takes coordinates and momenta. So the points in the configuration space here are gauge fields A. So they are these one forms on the principal bundle with values in the Lie algebra of the structure group. Electric fields are then velocities, right? That's what I said. They are in the kinetic part of the Lagrangian. So they are actually tangent vectors to gauge fields. Okay? And what we're going to do is we're going to impose boundary conditions on those tangent vectors, the electric fields, and on the curvatures of the gauge fields, because the curvature is the magnetic field. Right, this is spatial curvature. And then we're going to see what happens. So we kind of would like to do this in some sort of gauge invariant way, because it's very difficult. Like, if you're already working in a gauge, and you impose boundary conditions, and you see that those are not respected by the gauge group, then is that because you were working in a gauge, or because there's something wrong with the gauge transformations themselves? So what we're going to do, we're going to use this theorem. There's basically a theorem. I mean, I guess the details don't matter. I don't have that much time. It says, okay, so what you can do is, instead of viewing gauge fields and their curvatures as forms on this abstract principal bundle, you can actually bring them down to M itself, but at a cost, namely that they will be forms taking values in the adjoint bundle instead of in just the Lie algebra. So the adjoint bundle is the associated vector bundle to the principal bundle through the what's called the adjoint representation. So it's the structure group G acting on its own Lie algebra by conjugation. But since in the abelian case, this thing is trivial, because then conjugation doesn't do anything. So if you're thinking of electromagnetism, it's quite simple. It just means that we are now looking at forms, not as things on P, but on space, time M, with values in, this adjoint bundle, which for electromagnetism is just the trivial vector bundle with its fiber, the Lie algebra. Okay. So these are some mathematical technicalities. You can ask me about it later. I'm sorry if I'm skipping over it too fast. But what we're going to do is this configuration space of gauge fields is that's going to be some subset of all these one forms on space sigma with values in the adjoint bundle, and its tangent bundle. I mean, this is looking very difficult, right? We're going to consider a tangent bundle to this infinite dimensional space of one forms with values in this adjoint bundle. It's getting very, very tricky. But of course, even in infinite dimensions, a tangent space to a vector space, so you need to remember that Q is a vector space here, because you can add one forms, you can just add them, or subtract them, or multiply them with a constant. The tangent space to a vector space is just isomorphic to the vector space itself. So this means that we can view the electric fields, these velocities, these tangent vectors, just as things that are themselves in the look like objects in the configuration space Q. Right? There's this isomorphism. So they are themselves just one forms on sigma. Okay. And then the Lagrangian is, again, the electric field minus the magnetic field. So this tangent vector, its norm squared, integrated over all of sigma, minus the curvature integrated and squared over all of sigma. And then we need these both to be finite. So if we would integrate over all of R3 and they were not going to 0, then that would be infinite. So we're going to say they need to go to 0, these electric and magnetic fields, at some appropriate rate. Okay, so in the article there's a whole lots of details about the exact rates, like -3 minus epsilon, r to the -3 minus epsilon for some epsilon greater than 0 and everything. So you could have a look at that, but basically the idea is these electric and magnetic fields need to go to 0 towards the asymptotic boundary, towards infinity. But let's look at the configuration space at infinity then. Okay, you can make this precise through conformal compactifications. If we allow just any old gauge field at infinity, then obviously there's this action of the gauge group there that doesn't change the electric field, but it does change the gauge fields. And the tangent space to that orbit is going to be infinite dimensional, in fact. So the gauge group is infinite dimensional. So if it's acting on gauge fields at infinity, it's going to have an orbit. That orbit is going to have a tangent space that is definitely not going to be 0. Okay, it's going to be infinite dimensional. But that is not allowed because we need all tangent vectors. Remember, electric fields are tangent vectors. We need them to go to 0 for the energy to be finite. So that's where this whole thing that answers your question is happening. You have this very weird situation that since a Lagrangian is always defined on a tangent bundle, I guess you need that to guarantee like these variational principles. You have this situation where if you impose conditions on electric fields, then since they are tangent vectors to some space, requiring that they be 0 at infinity, you need that configuration space itself to be 0 dimensional at infinity, right? Because only a 0 dimensional space, so a discrete space, has 0 tangent space. Any space that has any dimension will have a non-zero tangent space, but that's not allowed because the tangent vectors need to be 0 at infinity. So this is why we need to actually put conditions on the gauge fields themselves. We need to choose some fixed gauge field at infinity so that there's only one element in that space, so that its tangent space will be just 0, right? Because it will be 0 dimensional at infinity, the configuration space, and then there are no tangent vectors. So yeah, the upshot is you need to choose a fixed connection at infinity, and you need to require all gauge fields to approach that connection. So one choice you could make is 0, and then you would get this. So there's this, in the non-abelian case, it's a bit more subtle, but yeah, I think I'm going to focus on the abelian case mostly. So yeah, this is what's going to restrict the gauge group to only the gauge transformations that leave these boundary conditions invariant, because we have picked one fixed gauge field at infinity, but any gauge transformation that's not constant is going to change that. So this is where you see these global gauge symmetries pop up, right? Because at least in abelian gauge field, the way it would change under a gauge transformation is you get the same thing plus a derivative of some gauge parameter. So it's only if we require gauge transformations at infinity to be constant that they leave the connection, the fixed connection we chose there, invariant. And that's why global gauge transformations at infinity are allowed. But all the others are not. Okay? So it's basically the idea is you have a boundary, an asymptotic boundary, where the gauge fields, where there's a fixed gauge field, and it must be unchanged by gauge transformations, and that's why you can only allow the global ones. Okay. Yeah.
So you're saying that if I pick some gauge field that doesn't vary at infinity, I can change the value of the Lagrangian?
Yeah, basically. Yeah, it's very weird. I know. So it doesn't actually have to be 0. Okay, so for the non-abelian case, maybe, but let's stick to electromagnetism. The gauge field at infinity doesn't have to be 0. It just has to be fixed.
Yeah, I understand, but if it's not fixed.
If it's not fixed,
Lambda equals
yeah.
r squared. Like, lambda, the function lambda is just equal to radius, distance from some.
Yeah.
Like the electric field and the magnetic field, they're not going to change anywhere in space.
No.
But the value of the Lagrangian is going to change.
So okay, so you have to be very careful here. So you're probably thinking, what the hell are you saying? Because in temporal gauge, the electric field is just a time derivative of A, right? Because normally it would be like 0 AI minus di A0. We're in temporal gauge. So you're saying, okay. Wait, sorry.
You give me value
Yeah.
of the gauge fields. You give me a solution of the
Yeah.
equations. I change it by a gauge transformation.
Yeah.
Where lambda is equal to r.
Mm-hmm.
Whatever you want. Then I
Yeah.
give it back to you.
Yeah.
And you tell me that that has a different value of the Lagrangian.
No. Okay. Yeah. So the equations of motion have not been imposed here. This is pre anything related to equations of motion, right? We are just trying to have a well-defined Lagrangian. We have not used the Euler-Lagrange equations yet. So that means that that E and A are entirely independent, right? If I would have a point particle at a location Q, then a priori, its velocity can point in any direction. And that's what I'm saying here, basically. Is that clear? Before any equations. Yeah, what I'm doing is I'm trying to even make the whole thing well-defined so that we could use the Euler-Lagrange equations. Because the problem is, if the Lagrangian is not defined on the tangent bundle, the Euler-Lagrange equations won't work properly. Because basically you would have too many positions in respect to velocities, or maybe the other way around, but you need this sort of one-on-one mapping. That's why you require a tangent bundle. Okay, any other questions? Yeah?
Just to make sure I understand this. Abstractly, I understand you're saying we have too many tangent bundle directions
Yeah.
compared to configurations.
Yeah, actually, yeah, or the other way around, yeah.
But how exactly do I see this? Like if I try to write down the Lagrangian, like what would break down? Like why?
Right.
Any physicist, I just try
Right.
to do it anyway, ignoring this.
Yeah.
What happens?
Okay, so what would happen is, suppose you would say, okay, I don't care. I'm not allowing only one fixed connection at infinity, I'm going to allow all the constant ones or something. So all the constant Lie algebra values it can take there. Then I know that space has, say, at least a dimension of the Lie algebra. So say, like, if it's SU2, like 3 dimensions or something. So I know the tangent space will have the same dimension. So it's gonna contain vectors that are not 0, because it's, for instance, 3-dimensional or 1-dimensional. So there's gonna be vectors in there at infinity that are not 0. So maybe just the vector that is like 1 in one of the directions of the Lie algebra and 0 in the other direction. If I would integrate the Lagrangian over such a choice of E, so one that is not 0 at infinity because it exists there.
Wait, right, but
Yeah.
why can I not just say, oh, I live my
So I am putting conditions on E that ensure that this is finite, namely that they go to 0. So maybe it's easiest to work with an actual boundary, because that in the conformal compactification picture you can do that. I have some space sigma, and this is like actual boundary. If I so if I integrate, suppose I have an electric field here that is non-zero, and I integrate that, then if this was a finite boundary, that would be totally fine. But since it's an asymptotic boundary, if I integrate, I get like this factor of r squared somewhere or something that makes that whole integral diverge. So if you consider a conformal compactification, you need to require like E on that boundary is 0. So that's the condition I'm imposing, okay? So then what precisely did you mean? Like,
I'm just wondering if it's possible to, for example, give up the tangent spaces.
yeah, okay, so that might be, so one thing you could try to get around this is say, no, let's just give up this very idea that the Lagrangian needs to be defined on the tangent bundle. But what happens then is what would happen basically is you might say, okay, I have a whole lot of gauge fields, more in a way than I have electric fields, because on those I've put boundaries. And then you can imagine maybe that you're going to get into situations where you have points, coordinates, but no velocities there. So you have no idea how the system would evolve from that point through time, because there is no tangent space there, right? You have no, normally you would need to be able to say, I have a point, there are all the possible velocities I could have at that point, and I'm going to choose the paths that set aside Euler-Lagrange equations, so that all have the right velocities everywhere to satisfy the Euler-Lagrange equations. But if I have a point somewhere where there are no velocities, you know, if a curve runs into that point, it's done, right? It's not a well-defined dynamical problem. So maybe, I don't know, maybe you could let that go or something. But I don't really see how you could work with any of the basic principles of the classical mechanics. Yeah.
Just briefly, so you say you want finite energy. Is it finite energy density or the total integral?
Yeah, so it's a total integral. So I have toyed with the idea that maybe you can just, in the end, redo it all by just requiring only finite energy density. Yeah. But then maybe you could say that there would be cosmological reasons to require finite energy or something.
Okay, so it's some mathematical convenience, but it makes a lot of sense physically. But
yeah.
So you could think of having infinite energy in principle, but
yeah.
the maths would somehow be wrong.
Well, I mean, I would not know. So I would not know what this integral is, right? It would be infinite. It would just be infinity. And so I would not even know, since this is the action, right? And since you get the Euler-Lagrange equations for that, I'm pretty sure they would be ill-defined themselves.
Oh, I see.
You see, but maybe you could try to, I don't know, go to some kind of more local description or something. Like you're only going to use the Hamilton equations or something. I have thought about that, but yeah, good question. Okay, yeah, I think I should probably not take too much longer, so I'm going to go through it a bit more quickly. But yeah, if you believe me, we've spent all this time just deriving the fact that we need to restrict global gauge transfer, the gauge group, sorry, to the ones that are constant at asymptotic infinity. And then we could use this whole constrained Hamiltonian formalism that I talked about earlier. So there's this idea of going to the Hamiltonian picture instead of the Lagrangian picture. Then you find constraints in the theory. If there is a gauge symmetry, it causes these constraints. So for the Yang-Mills theory, that constraint is called the Gauss law. It says that the curvature of the electric field is 0. So this is mathematics notation for what a physicist, they would write this. So this is the Gauss law. That is the constraint of Yang-Mills theory. And in the constrained Hamiltonian formalism, there's this idea that the constraints actually, they come from gauge symmetries, but they also generate the gauge symmetries. So what that means is if you take a Poisson bracket of the Gauss law together with a field, it gives you precisely the transformation of that field. Or if you want to be a bit more mathematical, you formalize that through what's called a momentum map. So my momentum map is literally just, it gives you momenta, like just the momentum p that you're used to. But it's a way to formalize symmetries in symplectic geometry. So on momentum maps, there's this particular definition here, which is basically, it's the mathematical equivalent of this Poisson bracket idea. And in Yang-Mills theory, the momentum map is supposed to be the Gauss law. Okay, that's how you formalize all this. And then what's called the constraint surface will be, so the C will be the zero level set of the momentum map. Right, it's where the constraints vanish. Okay, so you would need to actually check this condition for gauge symmetries, or the ones with respect to boundary conditions. So if you do that, if you calculate the whole thing, you can look at it in the article, you find that you need to do this partial integration somewhere. There's this boundary term that shows up. I mean, you would find that just from calculating this Poisson bracket. You find this boundary term, it's the electric flux through the boundary. So it's the electric flux through infinity or through the finite boundary, if it would be a finite boundary. And that boundary term has to vanish for the constraint to generate a gauge transformation. Okay? You can just show it only gives you the right transformation behavior if this boundary term is zero. Otherwise you get some extra term that wouldn't normally be there. So basically, through the constraint Hamiltonian formalism, you can derive that you need all these boundary terms, so the electric fields smeared by the gauge parameters lambda, you need them to vanish. And that requires that the gauge parameters themselves vanish on the boundary, because you want to be able to do this for any electric field. So asymptotically speaking, that would mean the gauge parameter needs to go to zero at infinity. So this gives basically this idea that before we derive that the boundary preserving gauge symmetries are the ones that become constant, right? And now the ones that are generated by the constraints that we will call physical are zero there. Okay. I mean, like I said, it takes a lot of time to actually make that all precise. You can have a look at the preprint for that. And then the quotient, yeah, it gives you the global gauge group, or actually in the non-abelian case, it gives you a copy of the global gauge group for every homotopy class of gauge transformation. So there's this topological aspect, but that's all right. And so we would like to now say, okay, so if we talk about gauge invariant objects, do we mean totally invariant, like under everything, under every boundary preserving gauge transformation? Or do we maybe mean only under those unphysical ones, right? The ones generated by the constraints. I would say we need to do the latter. We need to, because the global and the local ones, they have a different physical status. So we want to make our fields such that they are invariant under the local gauge transformations, but not necessarily the global ones. And this is where we can use this whole dressing field method. So basically, what you can do is you can project gauge fields onto this object right here. This corresponds to what you call the Helmholtz decomposition. And this is precisely the part that is invariant under all local transformations, but not global ones. Why not global? Well, the local ones, what would happen is you get, this A gives you this extra del lambda, and then you get two dels, and this is the inverse of the Laplacian. So that is going to precisely cancel the change in A. But for global gauge transformations, A is not changed here. So A is not changed, so this whole thing doesn't go through. And basically, okay, yeah, sorry. So A is also invariant under global gauge transformation, but you see, in the case of the global ones, it's not because it was sort of cancelled, it's because A was invariant all along. So that is okay, fine. But then if we add a Higgs field, it is there precisely to feel this difference. So the gauge field A wouldn't feel it, right? is invariant. This object, the projected Helmholtz part, is the radiative part, as they call it, is invariant under both local and global gauge transformations. But if we consider the Higgs field, it does feel those global gauge transformations. So what we can do basically is we can say, okay, we're also going to dress the Higgs field with that same object, and that will make it invariant under local gauge transformations, but not global ones. Because like I said, here you don't feel the global gauge transformations, but the Higgs field does feel them. So, I mean, we discussed this yesterday in the van as well, back from Slovenia. It's sort of like God put the Higgs field in the universe in order to be able to feel the difference between global and local gauge transformations. Or at least to also feel the global transformations, the physical ones. Yeah, so there is a bit of a subtlety with like the boundary conditions of the gauge field. I'm not going to get in of the Higgs field. Sorry, I'm not going to get into that. But basically, what you will find is there are two phases. You could either say what I call the vacuum, so zero energy, is when the Higgs field is actually zero. In which case, that vacuum is invariant under all gauge transformations, or even the dressed Higgs field. Or you could say, no, I'm going to call a minimum of the Mexican hat the vacuum. And then the Higgs field, even the dressed one, will feel the global gauge transformations. And so what Struve did in the end, he used this dressed Higgs field and the dressed gauge field and reformulated the entire Higgs mechanism in those terms and showed that it leads to exactly the same thing. So I think this should be thought of as the physical content of the Higgs mechanism, because what we're now breaking is this physical sort of asymptotic global symmetry group instead of these local ones that are generated by the constraints. And yeah, you can relate this to symplectic reduction in symplectic geometry as well. So you can ask about that if you're interested. Now, this is actually the one picture by ChatGPT. I thought it was really good. I asked it like, create something that sort of shows the transition from classical to quantum, and it has the apple and the waves, and then here it also has waves, but they're quantum waves. Yeah, pretty cool. So I'm going to be wrapping up, but basically what I've included here is that if you would use the axioms of algebraic quantum field theory and define spontaneous symmetry breaking in that way, and then you consider only spontaneous symmetry breaking of the vacuum state and internal symmetry, so a gauge symmetry is an internal symmetry, and you use the Weidmann axioms as well, then you have this really big and beautiful result, as Trump would say, which basically shows that, so there's a bit of technical stuff about how the Gauss law doesn't really work well with locality, but you get this result where you have a field algebra of Coulomb fields, so fields in the Coulomb gauge. Oh, by the way, the Coulomb gauge was precisely the one that was giving you all these dressings that I was talking about earlier. If you do that, then there are basically two options. Either the spectral measure of the electromagnetic field contains a zero contribution, so we think of that as there being massless vector bosons. In that case, I guess the most important part is the part that you don't see really well here. You know, the symmetry is unbroken, and the electric charge is what's called superselected. In the other case, because the global gauge symmetry is present, which leads to the superselection of the electric charge. In the other case, when the symmetry is broken, in that case you don't have superselection, but you have this thing called current charge screening. So basically, when you take the currents of fields and you consider how they fall off towards infinity, they go to zero, and that somehow replaces the charge superselection rule. But this is the stuff I don't quite know how to interpret. I mean, you can find all the proofs in my thesis, but yeah, there's still a bit of interpretational work to do in the quantum theory case, and this also relates somehow to quantum reference frames. So yeah, to conclude, I've basically presented this idea that the Higgs mechanism should be understood as an instance of global gauge symmetry breaking because those have a different physical status. But I do have to admit, I haven't said anything about how that happens dynamically. So how the Higgs actually results in the electroweak phase transition shortly after the Big Bang, and how that happens dynamically, I mean, that's a huge open question. Like, no one knows that. But I think that at least what we've done is, so there's this general question of how spontaneous symmetry breaking happens. It's related to the measurement problem and how you can go from a symmetric to an asymmetric state if you have only symmetric evolution and those questions. So there's this general problem, and I think the Higgs symmetry breaking is now like not any more mysterious than the general problem, spontaneous symmetry breaking. And we've done that by interpreting it as global gauge symmetry breaking instead of local. So yeah, that was it. If there are any questions, I'm happy to answer them. Thank you.
All right, thanks for the great talk. We should use the microphone so that people who are online can also hear the questions. Other questions? Okay. Just one before I forget.
Yeah, of course.
So just for my understanding, I'm trying to puzzle some pieces together in my mind now. In the classical case, when you look at the, say, the asymptotic GI group, is it abstractly isomorphic just to the finite dimensional group that you begin with, like U1?
The quotient is.
The quotient.
Yeah,
the quotient is,
okay.
yes.
So GI is still huge because it has only conditions at infinity.
Right.
So GI is still
mod
huge.
G0 infinity.
And then there's this one,
Yeah.
So this is what I use as notation for the identity component of this group generated by the constraints. And this is just isomorphic to, okay, I mean, if it's U1, it's U1. If it's SU2, it's going to be like Z times SU2, because SU2 is just S3 topologically speaking, and in here you have the, because you're working on three-dimensional space, you would have to consider the third homotopy group of that group. So in this case, that would be S3, would be Z. Yeah, okay. So you have these topological contributions, but apart from that, it's always just a copy of this original structure group that you started out with, the finite dimensional one.
Right, thanks. Actually, one follow-up, abusing my role as a chairman, but I have to think a bit more about this, just spontaneous. Maybe we can chat about this afterwards, but there's some of the idea that, so you have physically equivalent descriptions, which would be the local gauge symmetries, but then you can kind of ask like how the global thing, the full system couples to the rest of the world or so. And this is somehow a shadow of gauge symmetry still remaining and kind of keeping some physical status. So could I think of this now here happening as well? That is, I have these G0 infinity that happens locally, that have like no physical significance, but still somehow the whole universe, right? How it would couple to something bigger or something that remains of physical significance. Like
I mean, I think one way to think about it is somehow you're actually putting yourself outside of the universe. You have an observer at infinity on that boundary, and that person can, sort of in a relational way, feel the global gauge symmetry physically, but not the local one. And this relates to this problem of gluing, where you would have two different regions, and you could even have that for finite boundaries. And you ask, okay, if I have matter fields in both regions that feel gauge symmetries, then if I know only local content, can I glue it together into one whole region? And then you find, yes, except for the global gauge symmetries.
Right.
So it's precisely, that's this result by Henri Gomez. And I think that is sort of what is happening here, but then like you're doing it for the universe and like infinity.
Right.
Yeah.
Okay, great. Thanks. More questions? Yep.
Maybe this is also a bit of a follow-up. I just like to understand better this boundary symmetry group, because you've kind of, if I think of it as just being something that would be accessible from an outside observer, I would naively expect it. Maybe I could also choose a different U1 group element on every point of the boundary. Whereas I think what you're trying to argue is that it has to be constant. Did I understand
Yeah.
it correctly?
Yeah, so that's a good question. So I think you're probably thinking a bit more in terms of finite boundaries, right? Like, suppose I'm here and I put a boundary about myself and I try to connect myself to the system, the environment, and try to glue those gauge. Yeah, then I see what you mean. I think you could probably do that. But in this particular instance, yeah, what happens basically is, yeah, so at infinity, you do need, you can only allow these constant transformations, because otherwise you would change the angular directions of the Yang-Mills field. So the Yang-Mills field is a one form. So if you do it in spherical coordinates, it would have this r direction, but it would also have these theta and phi directions. So you would change those if you would allow the U1 element to sort of vary over the band. And then it turns out, by the way angular components of Yang-Mills fields transform under conformal like rescalings, these varying angular components at infinity would actually carry infinite energy. So in this particular instance of asymptotic boundaries, so this is where I think asymptotic boundaries might actually be different from finite boundaries. In the finite boundary case, I could see what you mean, but for the asymptotic boundaries, yeah, since you're so far out in infinity, if you would allow that, yeah, you will see through the conformal picture that would actually, yeah, create infinite energy somehow. Does that answer your question, or?
Okay, so you're saying these would actually change the physical observables in a way that the energy merges?
Yeah. Yeah, I think so. So the problem is infinity is very difficult to talk about because it's not an actual place in a way, right? So the best we can do is say we do make it an actual place through a conformal compactification. And then we need to take into account that whenever we do an integral, we have some conformal factors in there. So if we integrate the electric field over that bound, so yeah, okay, so first of all, if you would allow the vanishing gauge transformations, they would inevitably lead to these non-zero electric field components in the angular directions. And then if you would do that integral over that boundary, then by the definition of a conformal compactification, you would get like an r squared in there or something. And then that would diverge if you integrate over, well, okay, maybe not r squared, but like 1 over r squared, but then you're integrating over r3, and then it would still be infinite. So yeah, that would be problematic. But maybe for finite boundaries it wouldn't. I'm not exactly sure.
Right, yep.
So this is a bit of a more speculative question or comment. So yesterday we tried to discuss how we can understand in this context the Higgs field as some sort of quantum reference frame for the other fields.
Right.
And just hearing this again now, I thought one aspect was really interesting, and that is that it seems there are the global gauge transformations which the Higgs field seems to transform under and the other fields don't, whereas usually when we have additional symmetries in quantum reference frames, it's that the reference frame is usually not sensitive under certain transformations, but maybe the other systems are. So usually we consider the reference frame to carry more symmetries, to not transform under certain transformations, whereas maybe the other systems we're describing do. And so then we call them non-ideal frames in that sense. And here it seems to be a bit of the opposite, that the Higgs field seems to be sensitive to something that the other systems are not. And I'm curious if you have any thoughts on how we could still view that as some sort of non-ideal frame, but sort of the other way around?
Yeah, I mean, that's a difficult question, but maybe you would have to look at the actual quantum state on that field algebra. So working like with the axiomatic approach to quantum field theory, maybe you could say, okay, yeah, I would somehow have a state of, like, okay, the fields themselves are algebra elements. A state assigns only expectation values to that. So maybe you could say, like, okay, I have some kind of state that serves as a quantum reference frame, which would be invariant, but then from that state, I would see that the Higgs field itself is transforming or something. But so it's a, I'm not quite sure how that works precisely, but yeah, I guess it's too simplistic anyway to say that the Higgs field is a quantum reference frame, because what is it? In mathematical QFT, the Higgs field is just an element of the algebra of observables, right? So it's actually an observable. So you would need to think about, yes, but what would a quantum reference frame actually be, like, precisely? And then maybe you could solve it. Yeah.
Any more questions? Okay, if not, then let's thank Sylvester for the great talk. You're around only today?
I'm here tomorrow as well.
Tomorrow as well,
Yeah.
okay.
So I heard there's I can take this off now, right? Yes. I heard there's a talk at 2.